Hello, everyone. We are starting lecture number 10. Sorry for being a little late. I had some technical difficulties today. So today we are starting a very, very long promised topic about profunctors. And I decided to start with a general motivation why profunctors are important. A little later, you'll see that they are important in every single way. But right now, let's start from this very baby motivation. So as you can see right now on my whiteboard, we have a functor phi that goes from a product of categories to categories A sub I to some category B. And in every component, our functor is either covariant, either contravariant. We can group together covariant and contravariant components. So in some components that is contravariant, we will take product of categories, again, category called it A prime. In some that they are covariant, we'll again take a product of categories, again, a category, so it's A double prime. And therefore, every functor of multivariable functor can be written as a functor from some category opposite cross some category not opposite to category B. So now it becomes covariant in both variables, taking opposite category on the first variable. This is the motivation to consider profunctors. So profunctors are functors that generalize both covariant and contravariant functors. However, I won't be considering the all generality of functors, and I will stop only with the functors that they land in category B, in category V. So in our base cosmos. In case of sets, this will be category of sets. And I am giving the first definition. Throughout this lecture, I will suppose that V is a cosmos. I will remind what is it. It's a closed symmetric monoidal bicomplete category, and it is equipped with tensor product or monoidal operation. I would say this cosmos, this monoidal operation, when I fix one variable, has a right adjoint which I call internal home, and it also has a unit of monoidal operations that I call I. So my profunctor, or more precisely V profunctor, I call just a bifunctor from category A op cross B to self-enriched category V. Yes, you see I have enriched categories and enriched functors, but every time you think about this and you do not feel very comfortable, you can think about a functor that takes values in category of sets, and this is just product of categories, the tensor sign between categories. I'm using the special notation. The special notation for this is is an arrow from A to B, but it's not a plain arrow, but slashed arrow. Other authors use the other notation. Some put circle in the middle of this arrow. Some put some other signs, but I will be using this one. Also by profunctor category, I mean category of profunctors from A to B, and I will denote it with also slashed brackets. So that's a notation for today's lecture and so on for profunctor category. I would say that this slashed bracket, that's my invention. Just I decided to be not so original. If I have functor category, just brackets, the slash brackets will denote functor category, profunctor category. Of course, if we have two functors, there are natural transformations between them. That's the second definition. And in this second definition, I will say that that natural transformation between profunctors, it's a natural transformation between the corresponding bifunctors. So arrow from P to Q, it's a natural transformation alpha between the corresponding profunctors. And I will be freely switching between profunctor and bifunctor. And when I use either of notions, you can you will see from the context. So once I'm talking about the category of profunctors, of course I think about this as a profunctor. If I'm talking about functors, just think about this as a bifunctor. Well, now it's time for examples. Well, the first example is identity profunctor. It's just given by enriched home functor. So you are taking, I'm reading right now here, you are taking this category and its opposite, making pairs, and the pair is going to the value of home, of enriched home on it. I will remind that in a realm of enriched categories, our sets of morphisms are not just sets, but objects of our base of enrichment, our cosmos V. Therefore, it is well defined. If you will have two abelian groups, then home between abelian groups, it's again abelian group, and this is an example of a profunctor. If you have two modules, then home between modules is an abelian group, and it's again an example of profunctor. Well, then I decided to give immediately very, I would say, not sophisticated, but super important notion of representable and co-representable profunctors, and they are defined using a given fixed functor. So if f capital is a fixed functor, enriched of course functor, V functor from category A to category B, then I can write B sub f and B super f, and they are called representable and co-representable profunctors respectively. How are they given? They are given by twisted home. So why I'm saying twisted home? Because in a home you are twisting either of components, either covariant or contravariant component. If you apply functor f to your covariant component, then you say that it's representable profunctor. That's the first case. If you apply functor f to your contravariant component, of course it's a co-representable profunctor. That's a second case. What is interesting here? So the set or object of morphism from object B to object f of A is a value of this profunctor. So every time you are interested in objects of comma category, if you remember, we had comma category from B to some f of A. So objects can be understood as values of the totality of such objects can be understood as a value of a profunctor at certain pair AB. So we saw this thing many times. This is similar about co-representable profunctor. The important thing is that when you are trying to write profunctor by twisting home, you always are thinking about the direction of arrows. So either arrows are going in from A to B or from B to A. Funny thing is the following, that representable profunctor change the direction of arrow, and co-representable keeps the direction of arrow. So if our functor was from A to B, then co-representable profunctor is still from A to B and representable from B to A. Why this is so? Because you can see how are which component of profunctor is twisted. So the first one is not twisted, then it is B. Second is twisted, then it is A, and conversely. Also, some authors use different convention when writing profunctors. I will return on the previous column, and will put op sign to category B. Some put to category A. I'm using the convention that op is used for the first for domain. That has big sense because, as you remember, functors are contravariant in their domain and covariant in their domain. When you are thinking about usual representable functors, that's the motivation why I prefer this notation. Are there any questions up to this moment? That's not very simple material, I think, from the first side. So please ask me any question anytime you need. Okay, since there is silence, I will continue. Well, the next thing is after defining functors and natural transformations between them and giving a couple of examples, the next thing is to give a composition of profunctors. You know that functors are composed just by a well, my computer somehow decided to a little play with it. So can you hear me? I will try to reload Zoom.
Recording in progress. Yeah, Alex, we can hear you now.
Can you hear me?
Yeah.
The main that the recording is in progress. Fine. Then we are returning to Profunctors. Sorry, I have no idea why did it happen. I wasn't violating any Google or Zoom rules. Maybe they think I'm a terrorist. So the next thing is to define composition of profunctors. I'm defining it using coend. The important thing to emphasize that I will be using the diagrammatic notation. What does it mean? I will put profunctors in composition as they appear in diagram. So first appear P then Q, then I will write P diamond Q. I want to emphasize that I'm using the diamond sign. People can use in their articles or books different signs, but I decided to keep this notation from coend calculus book. So composition of profunctors should be a profunctor from A to C. So we need to get rid of the variable B. My profunctor P is covariant on B and profunctor Q is contravariant on B. Therefore, I can make a pair which becomes a bifunctor from B op tensor P to category V, and for fixed A and C, and take a coend of it. The coend of such bifunctor will be their composition. Or other way, it is a convolution. It is pretty much a convolution. Okay, so you can think about this as that you are just convolving on a common variable. I will give you a couple of examples a little below why composition is precisely this way and how you can relate your profunctors to the things that you already know. But before that, I would say that composition of profunctors is not associative. However, it is weakly associative. So you have a natural isomorphism between the triple composition. So for functors, we had triple composition being associative, just as for functions in calculus. For profunctors, that's not so. Why? One of the reasons is that we are making a choice of universal object, which is called coend. This choice prohibits us to make so bold statement that we have the unique object. So going different ways will give us different object, but they will be canonically isomorphic. The second thing is about the composition being not strictly unital. So we can compose our functor with an identity profunctor. Identity profunctor was defined already. It's a hom. on either side. And as you see, I just wrote why this is an isomorphism. It's because of covariant and contravariant UNEDA respectively. So if you will write down what are you doing with your profunctor, what is the composition, this coend, then you will see covariant and contravariant UNEDA lemmas respectively. Nothing else. So contravariant and covariant UNEDA, surprise, surprise, can be also given in terms of profunctors in this way. Okay, and just before going a little deeper, I want to summarize and tell that the totality of all small v categories, profunctors between them, and natural transformation of v profunctors form bicategory. Bicategory is a weak two category. Once we had a category of small categories, it was two category, but in the two category, all associators, uniters, and so on were trivial, so they were identities. Right now we have certain isomorphisms, and these isomorphisms should satisfy certain compatibility conditions, so-called coherency conditions. It's similar to monoidal categories, some pentagons, some hexagons, some triangles, and so on. So this is a weak form of two category. It's called bicategory. Working with bicategories, you should be careful, as not always equality is actually equality. So your diagrams not necessarily commute, but they commute up to certain isomorphism. Either canonical, either unique or not, you need to think yourself. But everything usually not commute, but is, how I would say, weakly commute. Well, for every bicategory of its general principle, there is a strict two category which is equivalent. I would say two equivalent to it, but that's other story. However, you can always think as this category of profunctors as something very familiar, for to which I will follow right now. Okay, so now I will write something that will help you to relate to it. So example. So suppose A, B are discrete categories. Then profunctor from A, pi from A to B is given, are, let's call, finite discrete categories, is given by matrix. Surprise, is given by matrix. So we'll have a matrix. So here are A variables. The results are in B. And this is our profunctor P. So if first category has M elements, second category has N objects, this will be M by N matrix. And on every spot in this matrix will be standing what? So will be some set. So it's given by matrix whose entries are sets. Moreover, when you have two profunctors, P and Q, then their composition, it's product of matrices. So you can organize for finite case of finite categories all your objects in a row and think about homes between from I mean, this P you can think as hom or natural transformations from one object to another, and that is always a set. And then convolution just gives you product over not product of these matrices. So what is a column by row? I think you can be a little confused. So column by row corresponds to, so Cartesian product is multiplication and coproduct is addition. So you can multiply such matrices in a usual way. Okay. Then second example. That's what I announced before, that profunctors generalize contra covariant functors. So case A, if trivial category to category B, profunctor P is a profunctor, then we have I opposite tensor B to V is a functor, but I opposite I, it's a trivial category with one object whose object of morphisms is given by monoidal unit, is isomorphic to itself. So it's trivial category with one object, nothing to op, and trivial category by any category is isomorphic to this category. We are just making a fake component at every single object. Therefore, P is given by functor from B to V. So it's covariant functor. Part B. If from A to I is a profunctor, then P from A op to V is a corresponding functor. So we have a corollary that profunctor categories from trivial category to B is isomorphic to functor category from B to V. Of course, when it exists, and profunctor category from A to I is isomorphic to category of contravariant functors from A to V. That's what we have just from the beginning. Okay. Then we have the following thing. We have example. We have bimodules. So part A in this example. No, before part A, general thing. So let lambda be an associative ring with identity. Then lambda can be considered as one object category whose object of endomorphisms is lambda. So we have one object, let's call it star, and we have arrows on it. These arrows correspond to elements lambda 1, lambda 2, identity, etc. So composition is given lambda 1 by lambda 2. It's a composition in a ring. It gives us composition in this category. Then addition in lambda makes, I need to move my screen, makes it ab enriched. Therefore, lambda, our ring, is one object category with lambda from star to star is given by lambda. So lambda belongs to abcat. So not vcat, but abcat. So we have now a cosmos of abelian groups. So every ring can be considered as a one object category and enriched in a category of abelian groups. Then part A. Functors from lambda to abelian groups. Additive functor. I don't like letter F here. My apologies. Let it be N. So suppose N is an additive functor from lambda to abelian groups. Then it takes star, moves it to some abelian group N, and it takes action, so R multiplication. It will go to R multiplication from N to itself. It's action on this abelian group N. And also it's additive. So it keeps sum of scalars. It is a functor, so it preserves multiplication by scalars. And also N is a abelian group. So together, we get that N gives us left lambda module. So left lambda module. Part B, if we will take opposite ring of lambda to category of abelian groups as additive functor, then similarly we'll get that M over lambda belongs to mod lambda is a right lambda module. So we have corollary immediately. that lambda to ab functor category is precisely lambda mod, and lambda op to ab is a category of right lambda modules. Of course, I won't stop at this point, so I want to join two things and say that if lambda gamma are associative rings with identities, then lambda op cross gamma to ab, let's call it H. This is additive functor. Then H and gamma is a bimodule. Lambda gamma bimodule. Oh, we'll write lambda mod gamma. This is a bimodule. So you can think of profunctors as certain one objective in a category of billions, or other way that every category enriched in category of billion groups is associative ring.
I can't hear. Sorry. I think you mute yourself, Alex.
Oh, really? I was muted all the time. Oh my goodness. Oh my goodness. Thank you, Shannon. Okay, so as I said that profunctors, I just will repeat my last sentence. Guys, my apologies. I don't know what is this technique. Oh my goodness. So profunctors generalize bimodules, matrices, covariant functors, contravariant functors, and relations. Also, I haven't said anything about relations. Maybe I should say a couple of words. So it's another example. Well, let it be example in red. It's really important. So if our category V is a category with just two elements, 0 and 1, it's symmetric monoidal category. Then we will have profunctor from A to B, and A, B are sets enriched, of course, not sets. Their categories enriched in V. Then profunctor P can be thought as generalized relation. Why? Because P of pair AB is 0 or 1. So 0 if there is no relation between object A and object B, and 1 if there is a relation between A and B. So they are generalized relations. In this way, they can be seen as this. And composition of profunctors is composition of relations. That's what you know from basic discrete math, how to make composition of relations. Are there any questions? Okay, if there are no questions, let's then move to another topic. Another topic, it's my know-how. It's called radiation category. Half a year ago, I decided that composition of profunctors should be related to something more familiar. And this object get name radiation category. Why, I will explain to you in a second. So let's think about this. So if, sorry, not red, but black, pi from A, right now just pure categories A and B. That's if it's ordinary profunctor, then for any A comma B, pi from A to B is a set. So elements of pi AB are generalized arrows. Why generalized arrows? If our pi is a home functor and A equals B, then we will have home from A to B in the same category, and they are really morphisms. And if A and B differ, but still it is a set, we can think about this as generalized arrows. So elements of PAB will be called formal morphisms. And morphisms of categories A, B are called actual morphisms. So if I will write arrow from A to B, this is a formal arrow. When I will write arrow from B to B prime by B small, this is an actual arrow. Composition of formal and actual arrow will be given by the following rule. So B times X, or just let's write it BX, BX is given by P A comma B applied to element X. So what is P of A comma B small? Is an arrow from set A B to A, B prime, and its value on element X is a new arrow Bx. If we have arrow from A prime to A, actual arrow A, and formal arrow from A to B, X. Okay, let me write there. This is Bx. We can, oh, pardon, that's formal. We can write arrow XA. What is XA? XA is a value of P, A small, B capital, at X. So it's just pre and post composition, as you already know from representable functors. Similar story I'm doing with not representable functors, where it was F upper and lower star, but here with B and A, but they are twisted by profunctor P, not by home functor as before, but by profunctor P. And what is the main thing is that why profunctors are also called by many authors by modules. Is generalized associativity. So if we have formal arrow from A to B, here from A prime, A, here is X, here is B, from B to B prime, then BXA equals BXA. If we put parentheses this or other way. This is by functoriality of profunctor pi, because profunctor pi is a bifunctor. Therefore, our profunctors are similar to bimodules. Well, then when I am trying to write composition of two profunctors, given object A in A and C in C, I am computing coend. I am reminding the formula. So it will be PAB tensor. Now will be not tensor, but cross. I'm using regular categories. Q, BC. So our Cartesian product is monoidal operation on category of sets. This can be given by the totality of all PAB cross QBC, so disjoint union over B belonging to category B, subject to some equivalence relation. So this is equivalence relation. What is that equivalence relation? So arrows, we have two arrows here. Here belongs to the first component belongs arrow X. So X belongs P from A to B. And Y belongs Q, B, C. We will write two formal arrows from A to B to C. This is X, this is Y. And we will write another formal arrow, a pair of formal arrows, X prime, Y prime. And here I will write actual arrow, B. So you say that X, Y is equivalent to X prime, Y prime, if and only if there is a finite zigzag of morphisms B from B to B prime, joining them. So instead of one arrow here, I could have many arrows. So if I have here formal, here formal, here formal, here formal, again, I'm writing a couple of formal arrows, then I will have one morphism one way, one another, one this way, and here all identities on the edges. And this means that in the middle, there is not just one morphism, but any sequence of morphisms going in either direction. If they're going in one direction, you can compose them. If they are going in opposite directions, you just leave them as they are. So this is a zigzag. And any pair of formal arrows, X, Y, is equivalent to any other pair on the same zigzag. So you can think about this as path in a category, path in a space from a pair XY to pair somewhere here, X prime, Y prime. And these arrows are given by such diagrams. Such diagrams commute. I forgot to say. They commute in the sense above. So here, these diagrams commute as composition of formal and actual arrows. Such diagram, as you see here, will be called procommutative. So you have a procommutative diagram. It's a diagram where you have arrows defined by profunctors and arrows defined by actual morphisms. So formal and actual morphisms constitute a diagram, and if any path in this diagram makes sense, I would say every part of this diagram makes sense as a procommutative diagram, then the whole diagram is procommutative too. Okay, so every square here is a procommutative diagram, and then the whole diagram is procommutative. So two pairs are equivalent if the procommutative diagram of zigzag, if the diagram of formal and actual morphisms given by this blue zigzag is procommutative. One can ask me, where have I seen it? I will answer you. If you have seen X functor and how UNADA constructs X functor by pairs, then here it is. If somebody knows, Tor functor is constructed exactly in the same way. So X from A to C going through B, where B will be, for instance, some projective objects or whatever, is constructed exactly in this way. But first you arrow your arrow is an injection, another is surjection, or monomorphism and epimorphism. And B belongs to category of projective modules. That's how you work. Okay. Other questions to this? It's very important thing. If you understand it, we can go further. If you have questions, please ask me. Don't worry. If you don't understand anything today or before, that's also okay. Just ask me a question. I can tell you where we are and what are we trying to do. Okay. I don't see anyone asking anything. Well, as you wish. So we have defined the composition of profunctors using some equivalence relation on pairs. And now I wish to, and we have seen here this procommutative diagram where we have pairs connected by pairs of formal arrows connected by actual arrow. I decided that this category deserves its own certain name, and this category I called radiation category. So definition. The definition is the following. So let A0 slashed arrow A1 slashed arrow A2 slashed arrow A3. Let me give just for 3 profunctors, okay? It can be done for any number of profunctors, even for just one. Let's write PQR are profunctors. Profunctors, A0 belongs to A0, A3 belongs to A3, are objects. Radiation category let's write how it's written. Red A, then I am putting vertical line pi Q R to here A0, here is A3. Has first bullet objects. Objects are triples of formal arrows from A0 to A1, from A1 to A2, from A2 to A3. And morphisms. Okay, my connection is not stable, so be aware that I can disappear for a second. And morphisms between triples. So let's call it X, Y, Z. Here is A1 prime, A2 prime. Here is Z prime, Y prime, X prime. Arrow here. Arrow here. Here is arrow A1. Here is arrow 2. This diagram is, every diagram is procommutative. Okay. These are morphisms. Trivial morphisms. When you have A1 and A2 are identities, give you identity objects. Composition is given by composition of vertical arrows. So composition equals composition of vertical arrows And this category will be called radiation category. Okay. So you have triples and they are connected in this way, that you are changing only middle objects. Categories A1 and A2 are called filters. That's how I call them. Why radiation? You have some radiation as bunch of rays going from emitter A0. It passes from A0 through certain filter A1, changed, then it passes through a certain filter A2, and then it falls on absorber A3. That's why I call it radiation. You can put how many filters you want. So here A0 is emitter and A3 is absorber. That's how you construct radiation category. Just from our definition, we'll follow the following statement. That pi diamond Q diamond R at A0, A3, this profunctor composition is isomorphic to another profunctor composition pi diamond between Q diamond R at pair A0, A3, and they all are isomorphic to some common thing, which is pi 0, so set of connected components of the following radiation category: A0, pi, Q, R, A3. So there is a common category. There is a common category whose set of path connected components. I want to remind you that path connected components are classes of equivalent objects under the equivalence relation of being joined by zigzag, finite zigzag. And so path connected components of this category are isomorphic to either of triple compositions. Is that okay? If you have two functors, I will have another statement that if you have A op cross C to category of set, this is a composition of functors P and Q, then you can factor this composition through pi 0. And here will be your red, blank, then P, then Q, then second component I put double blank. So composition of profunctors factors through the category of small categories. Cat. You can think about radiation category as the categorification of the composition of profunctors. If you would like. So this was categorification. Categorification of composition. Are there any questions? Okay, then let's go. The next thing that we are going to do, we have still 20 minutes, will be representable functors and radiation categories. So let me call this topic. I would call it core bridge categories. So in certain situations, radiation category for simple cases of profunctors turns to be simpler, and I will call it bridge or co-bridge. You will see why and what is it. Okay. So let's consider some example. Let me have from A to B functor f, from C to B functor g. That's my situation A. Then I will turn either of profunctors or either of functors into profunctors. What will I do? I will apply co-representation to f, so I will obtain B super f, and I will apply representation to functor g, and I will obtain profunctor from B to C. So it will be B super g. Right now, nothing is enriched. So here we have a so-called, wait, is it a span? It's cospan. We have a cospan or span. No, that's a cospan. And here we can take composition. So what is our composition? BF diamond BG at point AC. It is given by coend over B. Here will be B FA to B cross D. Here will be again B. Here is GC. By Koyaneda. Koyaneda tells us that we can make convolution on a free variable in with a home functor. So with this we are making convolution and substitute instead of this B our f of a. This will be B FA to GC. So as our composition BF BG is isomorphic to B FG. So this is a new profunctor. Now let's think about formal arrows, formal morphisms. So formal morphisms. So X belonging to B FA to B. What is it? It is an arrow from FA to object B, arrow X. Then Y belonging to B from B to GC is an arrow in category B from B to GC. And now we know that in radiation category, red from A, then profunctor B super F, then profunctor B sub G, then object C, we have that we have a pair FA going to B, going to GC. This is your X, this is your Y. Isn't it familiar with something? I think it is familiar. So you are factoring your maps between the images through a certain category B. But then I will use what I will say homotopy theory. I can make my path, I can shrink my path. So I will write arrow Y again down. It will be here GC. Here will be equality, here GC, here is equality, here is equality, and here will be YX. So this is the diagram that is commutative in category B. So any X comma Y is joined in category red with pair YX comma 1. Or equivalently, if you want, with 1 comma YX. This is also possible to do, just making the other equivalent. So again, so conclusion. Our radiation category A, B super F, B lower G, C is equivalent to B, F of A, GC. It's a discrete category. If A comma C vary, we obtain that we have arrow from A to A prime. Here will be FA, FA prime, GC, GC prime. Here is X. I will call this common X. Here is X prime. Here is F of A small, then G of C small, and from C to C prime, C small. Something that is that reminds you comma category. That's right. Something that's really as a comma category, but here you have some other object. Okay. Then define F nabla G at AC to be this radiation category and it has objects. Objects are triples A, then map from FA to GC, C, and obvious morphisms. F nabla G at pair AC is called bridge. bridge category. From F to G at A, C. Okay, then let's define dual thing. Dually. If we have category B, here category A, here is category C, here is functor F, here is functor G, I'm turning it into A, B, profunctor to C. Here will be A sub F, there will be C super G, and then composition A sub F, composition C super G at pair AC will be given as pi 0 of so-called co-bridge, which I will define dually to the bridge before. At AC, this is called co-bridge category. So how is given co-bridge? We have A, then arrow from A to FB, then we have from GB to C, and then we have C. Well, and I would say that here we have a and B. Here on A is equality. Here FB prime, GB prime, comma, C, C, A. So co-bridge has objects pairs if A and C are fixed, from A to image of F, and from image of G to C, but image is under the same B. So here are bridge and co-bridge categories. Okay. Then let me write some simpler things. So or not, 1 second. We'll need bridge and co-bridge a little later. Okay, now proposition. Two functors A from A to B and R from B to A are adjoint if and only if. You remember the statement, B here, LA comma B is isomorphic to A, RB. But this is the same as BL is isomorphic to A sub R as profunctors. So profunctors are, so functors are adjoint if and only if the corresponding profunctors are isomorphic. So the statement about the adjointness of functors can be reformulated in this way. Or you can say that functor L has right adjoint if profunctor BR, so functor on the left, is, we are looking at the functor on the right, is representable. Functor R has left adjoint if the corresponding profunctor, looking on the right, is co-representable. So adjointness can be described in terms of representable and co-representable profunctors. Okay, then what? Since we don't have much time, but I still want to use it. That what I would do. I want to describe you two notions. I want to describe you two notions that will help us to connect well-known constructions with my bridge and co-bridge. So first one will be comma category of profunctor. So of a single profunctor P from A to B. So what it will be? Comma category. Objects are triples A formal arrow X to B, comma B, and morphisms are A prime, here A prime arrow going A, sorry, here is pro arrow, here is B prime, B prime, B prime, B, no prime here. Here is X prime. And this diagram is procommutative. So comma category of a profunctor looks as comma category of a functor, of a pair of functors, but instead of a single arrow from A to B or images f of A to g of B, we have a formal arrow X. Notation. As for case of comma categories, we will write A, arrow down, then profunctor P, then category B. Of course, you can see the trivial cases when your profunctor P is representable or co-representable. You can derive them yourself. Then the dual notion is co-comma category. Co-comma category. Co-comma category will be defined in the following way: that objects are objects of category A, disjoint union is objects of category B, and we say that co-comma category, let me write this co-comma category as C. I will give a notation a little later, that C from X to Y is given by A from X to Y if XY belongs to category A, B from X to Y if X and Y belong to category B, and profunctor value from X to Y if X belongs to category A and Y belongs to category B. The only case left when they belong to opposite side. So X belongs to B and Y belongs to A. In this case, it's an empty set. I will write this category. I will draw this category. So I would say that here is your A. Here is your B. So here are some objects. Here are some objects, and arrows from A to B are given by bunches. So here is P, A, B. So it's not just one, but it's a bunch of wires going together. It's a whole set. So it's this whole set. You're not looking at one, but you're looking at a bunch of them. So you glue them together. And the blessing of the category of sets is that we have an empty set. If you are working with what? With a general enriched category A and B over Cosmos V, you do not have empty set, as only set has empty set. If you work in abelian groups, you do not have empty group. Your group has always 0. So here, the empty set helps us to cut away arrows from B to A, arrows that go in backwards. Otherwise, we can't do this. So co-comma category, as well as comma category, exist, and they are correctly given in a case when our Cosmos V is set. And to finish today's thing, oh yeah, I need to give a notation. So notation here, A, co-comma P, B is for co-comma category. And the thing that I wanted to give you, it's the following theorem. But wait, I haven't defined graph and cograph of profunctor. One second, guys. I will just check with it. Probably we will do this next time. But if it's quick enough, we can write it already. 1 second. Okay, I think we can finish with a theorem. So let's write this theorem here. We have an adjunction. How is it given? We have let's call it cograph, going from profunctor category from A to B is adjoined to cospan from A to B, and in opposite direction is going pi 0 composition bridge. And we have another adjunction, pi 0 composition co-bridge, going from span from A to B is adjoined to profunctor category from A to B. And here is graph. So what is cograph? Cograph is our co-comma category of profunctor P together with projections to together with injections. From category A, we can inject in it, and from category B. These are two functors. Graph gives us the opposite picture. Here is your comma, and from comma you can project on the first component and on the second. This is called bottom, this is called top, this is called domain, as we had before, this is called codomain. So we have statement number 1, statement number 2, and we have statement number 3. And it is the following, that a regular co-comma category from span from A to B is adjoined to cospan from A to B, given by comma. And also we have a corollary that any profunctor P can be decomposed as it's as a representable, co-representable. And in the similar way using comma A domain and then B codomain. This last thing is span and cospan representations of profunctor. This corollary. And the theorem above tells you that cograph and graph of a profunctor are related, where cograph and graph can be understood in the usual way that people use it. But in our case, we define them using comma and co-comma cat. If you want interested what is comma and co-comma, comma is composition of these two, and co-comma is composition of these two right adjoints. So graph of pi 0 of Nebula, let me write, graph of pi 0 of Nebula or bridge equals comma, and co-comma is a cograph of pi 0 of delta of co-bridge. So we can play with our diagrams any way we want and change arrows in any direction we want and get profunctors. And these profunctors define the whole situation. And any profunctor can be decomposed. It's a corollary using comma and co-comma categories as composition of representable, co-representable, representable, or representable and co-representable. So you can do whatever you want with profunctors, and this is the moral of today's story. Thank you so much. Sorry that I took you more than was promised. Okay, my camera is working. Yes, my camera is working. So now you can see me. And thank you for your attention. Are there any questions? Comments? Or I see Sean. Okay, we'll stop demonstration that I will see everyone. We'll have a gallery. Sean, Rahul, Ellen. Well, we did a lot with profunctors. That's definitely not everything that they want. Next time will be a little more. Also, I have a little depth on can extensions. So next time we will finish a little on profunctors, and probably I will think about can extensions. Maybe we will skip it, and we'll start weighted limits, co-limits. Weighted limits, co-limits will generalize everything what we had before. Can extensions, Unad lemma, any adjunction, whatever you have, limits, co-limits, everything will be given by weighted limit and co-limit. And there, profunctors actually play a huge role. There we will need them as weights. That's one of the things, that not to tell the same story twice. For covariant and contravariant functors, we join them together in the thing. So that's it. Okay, I will stop my okay. Wait a second. Now I don't know how to stop. Okay, so by everyone, if you have anything to say, you can say. See you next time and have a nice weekend.
Thank you.